So seems recording has not. Yeah, thank you very much. Okay, so today we'll be discussing about a new topic uh, that is on ensemble learning, and its reference is in this Alpedin's book. You can go through chapter 17. Now, the motivation of this particular uh, uh, approach is that uh, there are different ways you can, as you have seen, there are different techniques by which you can learn a model for the various kind of tasks, in particular the classification tasks. Now, every model has its own advantage and disadvantage, and particularly uh, in certain contexts, some models are more appropriate than the others. But whatever may be, uh, one of the thing is that there is no panacea. That is, there is no a single approach which will give you the perfect answer to this problem. So, uh, I mean, you will find that some models are better learning of the discrimination of certain kinds of objects in a particular class. So some specialties will be there always. And this is captured by this particular type of philosophy or in the form of a theorem, that no free lunch theorem, which tells that there is no single learning algorithm in any domain which will always induce the most accurate learner. So every algorithm has its certain limitations to provide you the perfect learner. So, like as one of the reason is that these algorithms are developed based on certain context, certain assumptions, and those assumptions may not be true in all cases, or may not be completely true in all cases. And there are also inductive bias that leads to error if the assumptions do not hold for the data. Similarly, with finite data, uh, I mean, you can have certain algorithms which is giving good result, but it may not capture the whole variance of the domain. So in that way also, your model would be limited. So what we rather consider that whether we can consider a combination of uh, multiple base learners. That means you you observe the decisions given different base learners. It is not that they will always agree, and there would be variations. So how best you can uh, exploit this situation, that so that because since there are many learners, and assuming that majority of them will be indicating the true result kind of thing. So that's an assumption. So you should be able to even get correct classification of some of the difficult cases. So the overall accuracy would be improved by this process. So that is the expectation. And based on that motivations, this ensemble learning approach is developed. So, but what are the issues when we combine these learners? Definitely, overhead of, there are overheads. Overhead means, as you understand, that you are working with multiple learners, so each algorithm has its own time complexity and space complexity. They would get simply added up. So you are increasing that space and time complexity. And sometimes, even it may not be, it may not given any effectively any kind of advantage. So both of them are possibly learning the same features, same thing, and one of them would have been sufficient to take a decisions. So it is not guaranteed that if you combine models, then it will increase accuracy. So it may also lead to confusions also in cases. So, because the weakness of other model can intrude into a strong model. So that is the problem. So you have a strong model and weak model combination, and then weaknesses will also introduce. So unless you uh, specify that what is the strength of the other model. Like overall, strong and weak combination would be disaster, I should say. So the key issues in this way is that we'd like to generate base learners that complement each other. That's what I was talking about, that if they are giving similar, if they're capturing similar characteristics, similar traits of the input distribution, both of them learning almost the same. And then there is no advantage of having multiple learners. Rather, if you can say that some learner is basically complementing the other, that means the characteristics which are not reflected, which are not getting discriminated in one of these learners, the other learner could capture it and give a decision, appropriate decision. There, this kind of advantage is there. So we have to think about that. No, how do you do that? How can you consider developing a set of learners so that you can judge that they are complementing each other? Then other thing is that, of course, that how do you combine the outputs of base learners? A very simple decision could have been, as we understand that majority decision may be one of the simple, but there are various other ways of combination. So that is one approach, but that may not always give you a good result. There may be other reasons for other kind of combinations. Even the combinations could be also parameterized. This fusion, decision fusion could be also parameterized, and you can learn also with respect to your data sets. So overall, we would like to maximize individual accuracies of a learner, and also we'd like to maintain diversity between learners so that they are complementary to each other. So there are different kinds of diversification. So I would mention a few. Like one is the different approaches, like different algorithms. Completely, you can use SVM, you can use Bayesian approach, you can use the decision tree. So there are different approaches, and each is performing the same task of classification, for example. So finally, the decisions what you are getting, they are giving the decisions at in the same decision. So they are performing the same task in the decision making process, but approach wise they are all different. So that is what different learning algorithms to train different base learners. There are different methods, parametric, non-parametric methods are there. Then the other thing is that even if you are using same learning algorithm, now as you know that there are various hyperparameters which has an effect on the performance of the algorithm, and it is very difficult to tune an algorithm with appropriate value of hyperparameter, which may not be always applicable on certain set of data in the domain itself. So we may consider even slight variations on the decisions. I mean, effect of hyperparameters. We may consider varying hyperparameters. We can take different decisions, and we can look at the consistency among them. Say some of these examples could be that number of hidden units in a multi-layer perceptron, the value of k in the k nearest neighbor, the error threshold, what you use for decision trees, the kernel function that you use for support vector machines, or even the initial weights of artificial neural network. So these are a few typical examples. Any question? So please mute your microphone. So the idea here is that once again, if you are considering at different hyperparameters, and then the errors variance and could be reduced. Like that is what you would like to observe, and then we can consider the different instances. So other kind of diversification. So one just I mentioned about the algorithms approaches. The other ones for a single algorithm, the hyperparameters could be varied to generate different kinds of models. Then you can consider your even the input data set. that could be also training data set, because it is very data dependent, your model. So if you have variations on your training data sets, you will get different instances of models. So accordingly, you can get different models. So you are again working with the same algorithm, but you are working with different training sets from the same data set. That means you are sampling them. So that is one. Otherwise, no, even you can integrate different types of sensors and measurements or modalities. That is another, like sensor fusion. One particular example is there, that video uplift movement to recognize speech, both audio and video uplift movement. So recognition gets more accurate, because you are taking additional information. You can consider random subspace. So use different feature subsets. So it's a different input representations. It is just not sampling, representation itself different. So different learners will look from different points. The random forest takes this approach because we have projections of data sets on different subspace, and you are training a decision tree, and then ensemble of these decision trees, they are giving you the random forest and the decisions you take from them as an ensemble method. It reduces the cost of dimensionality, as you can see, because you are working on a project. Now, the other diversity, this is what I was talking about. I was talking about different training sets. So that was representation, and this is training sets. In fact, this was I was referring to. So here, different subsets of training samples could be used, and this technique is also called bagging. This approach is called bagging, where you work on different subsets, and you can look at the consistency of your model of the decision process, and accordingly, you can design a classifier and ensemble classifier. You can consider also that if you are training the data sets, these training sets serially, that means easier samples are classified and then hard samples are classified later. And in this way, each one is giving base learner. So each one is working on on the different parts. So there has to be certain kind of decision making order that is also implied by this process. So this kind of process is known as boosting and cascading. This kind of approach. It tries to generate complementary learners instead of leaving this to chance. So this is what. The other one would be that you are partitioning your training space, because in different partitions you are expecting they have different characteristics. So each one could be handled by different learners. So which means now you are considering different base learners, and each one is acting like an expert on a particular domain. So as if certain base learner is specialized for certain kind of samples. So it is a mixture of experts that you are considering. So this is you can say that we have to check on this, that you have to consider the diversification of your ensemble of models, of your team of your set of models, and then of course you see that whether it is helping, whether it is giving accuracy. So that base learner to be simple. If it is simple, it is not chosen, as I was mentioning earlier. Now that combination of strong and weak may be disaster in certain context, but if you know that strength of every learner, or if you assume that there are certain strengths and then you are combining them, that would be helpful. Even they are weak learners. So it may be that they are not so accurate. I mean, slightly accurate in the sense they are at least working more than 50% of the accuracy, and but a combination can give you a better classifications, improve the accuracy, overall accuracy. So this is possible, and also base learners to be diverse. That means that sorry, specialization on a particular subdomain. That is, say, cascading, boosting, those techniques we are considering. So there are different kinds of combination schemes that we can think about. I have just given one example, that example of majority voting, but no, you can have different kinds of combinations. So first thing is that you are assuming each are working as a multiple experts, and they are working in parallel, or even they are working in cascaded manner. So there are two approaches. One is global approach, where all learners produce output given input and fusion of decisions are taken, like voting and stacking. And local approach, so that is what, like kind of cascaded one. Selected learners, mixture of experts produce output, which means now you have to consider that now what kind of learner you'll be using for a type of input. So there has to be additional characterization of input based on which you should select a learner or a set of learners. So multi-stage combinations also could be there, like those two, like a serial approach where you are. This is what this boosting or cascading and also cascading approach it does. That you are learning base learners in cascade from simpler to the, I should say, from easier to harder instances to learn harder instances. So base learners sorted in complexity, and complex learner used if preceding simpler learners not confident. So there is certain kind of confidence measure. We'll see that this is a cascading approach. So you during testing, you also measure the confidence of your decision. If your confidence is not good, some threshold could be. There are ways you can get confidence measure. Even the posterior probability is a measure of confidence. I told you in a decision. Though maxima posterior probability map approach, that's the Bayesian approach, can give you a decision, but the posterior probability in absolute terms reflects the confidence of that decision. So similarly, there could be other measures also. So if your confidence is not so high, you go for more complex models. So this is the cascading approach. So let me reflect upon some of the decision fusion process. The L learners, so consider there are L learners, and I'm using a bit abstract notations here. So let us consider the decision for the jth learner using that learner is MJ, that is a model, and X is the input vector. And this decision is expressed in this way, right? This is a decision. So decision could be binary, 1, 0, decision could be 1, -1 for a classifier. Decision could be a class number, right? So it is context, under different contexts you have to consider this. Mostly we'll be considering either 1 or -1 or 1 or 0 kind of decisions. Now, you have in decision fusion, what you do that finally you have to make a decision out of all decisions from L learners, and then you should take a single decision. That means, suppose it's a binary classification, so decision would be either 1 or say 0 or 1 or -1, the way you have designed the classifiers. And then you get all these decisions from different learners. And then finally, you have to decide that which class it is. So that means either 1 or 0. That is the final outcome. So why is that? And you know that decision-making process also requires certain parametric computations. It may have certain parameters. That means, for example, the weighted combination of different decisions, the weights itself becomes the parameters. So phi is the set of parameters. And y is the final prediction of combined learners that I mentioned. If we consider there are k classes, that means k outputs from each jth learner. So the decision on a feature vector x can be expressed in this way. That means, say dij, it could be a binary variable. Like it is expected one of them would be 1 and other would be 0, or one of them would be 1 and other would be -1. Right? So given a particular L8 learner, you can see that you can express decisions in this way. Right? So if it is a binary variable like this. So you get a decision for the ith class, right? For the ith class, you get a decision from L learners. So some learner may say it is ith class like 1, some may say it is 0, that means no. But that is for only ith class yi. Similarly, for k number of classes, you get so many, you know, outputs. So there are actually k outputs out of this process, out of this fusion process. One of them should be 1, all others should be 0. Those are the kind of constraints on your decision output, but it is in general, you can consider, different ways this decision could be mentioned. So idea is that predict on y is, for example, assign ith class if yi is maximum. So if it is working on other kind of thing like posterior probabilities, maybe we have to consider decision fusion to provide the posterior probabilities of the class given that sample X for that class, and then use a Bayesian inference, like use a map approach to assign a class to a sample. So just schematically, we are showing here one simple way of combination, and that is voting. You can see that decisions are weighted. So each decision is a kind of a numerical value, say maybe 1 or 0, maybe 1 minus 1. And weighted combination means each one will have certain weights and sum of weights should be equal to 1. That means it's basically weighted average of all these values. So you can see that depending upon the discreteness of the value or depending upon the range of the decision process, this weighted average will remain in this range. And then you have to consider that what decisions based on that score you are going to make. So, but y will be finally a score as a weighted combination of all these decision scores from different learners. And the way you are using, that's up to you. So if you are using, for example, 1 or minus 1, they are weighted combinations. If you are saying, say, it is positive, means you should classify it for the class representing 1. If it is negative, say, classify it for the class represented by minus 1. Similar kind of. So it's effectively it becomes voting if all weights are equal. Now, so there are different classifier combination rules. I have just provided one such example, but no, you can consider that weighted average, you can consider average or sum, you can consider max, mean, median, product, and different ways you can combine them. And as we can see that some rule most widely used in practice. So majority to class or plurality principles for multiple class, where you know that for every class you compute a score and then assign the class which has the maximum score. You can use also median rule for more robust to outliers the other way, and then minimum and maximum rules as respectively for pessimistic and optimistic approaches. Product rule employs each learner veto power, so which you are ensuring that more or less you are getting consistent results from every learner. Then only you are taking a decision. Otherwise, you are not. Something like that, right? And as you can see that it not necessarily sums up to 1. I just mentioned one typical case where you may get, but you have to take a decision. Say if 1 and minus 1 are two values for two classes, so you are expecting rather if you have more number of ones, so your average or sum will be positive, otherwise it will be negative, something like that. But they are not exactly 1. I mean, there are, finally again you have to take a, you have to define a rule by which you take the final decisions of class assignment. Now, with this respect, we can again revisit the Bayesian combination rule. I have already previously, while discussing about Bayesian inference, we discussed this matter. If you remember that if you have many hypotheses in the hypothesis space, and each hypothesis is providing certain posterior probabilities. That means each hypothesis is a is itself has certain posteriors. So you can take the weighted combination of posteriors. In fact, use those posterior itself in hypothesis uh, and take the respective decision out of that process. So the same thing will be visiting here. You can see that in the Bayesian framework we are using for posterior, but rather we are more comfortable. Yeah, we are using certain uh, priors. That Wj is probability of that model, which model you are selecting, and Dij is the. Let's mute your microphone. And Dij is a class posterior probability, right? So that is what. So finally, when you are considering, so you are getting posterior probability from different models, and then the combined posterior probabilities for the class is the weighted average. So you are expecting that, of course, since there are say finite set of models, so sum of probabilities of selecting any model should be equal to 1. So that's how you get the posterior probabilities. So choose only those who have so high PMJ, and you can normalize it, and you can also get a posterior. So it can be shown that if it's classified, if probability of error is less than half, but with the increase of number of classifiers, accuracy increases by majority voting. That is a kind of theoretical analysis is there, and you can. I mean, that is a paper you can refer. I have referred. You may go through that paper. Now there are few things which are interesting to note during these combinations, like how are you going to make your decision more robust? That means the variations of performance of a particular learner, you are reducing it. So we are assuming itself this the decision from a learner, that itself is an IIT, and with the expected value is that expectation of that decision and its variance is that. And for simple average, you can say 1 by L, and Wj equal to 1 by L. So expectation of your Y could be written in this way. So, expectation of your decision, which means it's a kind of robust. Uh, it's a robustness of what you are doing, and you can see that your expectation of Y is considering the expectation of DD. I think it is basically discussing with respect to bagging. You have multiple instances, for example, and then if you are doing the average of that, so in your space you are achieving the expectation there itself. Whereas the variability is also reduced, as you know that variability is but expectation remains the same, but since you are taking average, your variance of that variable is reduced by is basically uh, reduced by 1/11 factor. Right? It is reduced to 1/11 factor of that, 1 by 11 factor of that. So variance gets quite reduced. And if you see that if they are not independent, which means say you have say if you think in terms of bagging, that means you have multiple uh, not only bagging, you have the multiple variations of the same learner. You have jth learner. There are multiple instances of jth learner that with different uh, for bagging you can have different training sets. Learner means the same after same algorithms or different hyperparameters, and each one is giving you a decision, right? So in your space, you have a statistical distribution of your decision given a sample. So that is what we are talking about, and it is with respect to a sample only. So there is a uh, in that space of uh, learner, uh, if there are L learners, so you have a probability distribution of the decision in that case, in that space itself. And there is an expectation, there is a variance that you are reducing. Now, these learners may not be independent because they are very correlated because of the hyperparameters and other things. So, in that case, you can consider the covariances of these learners. So, all these things can be measured with respect to your training set. What is the performance on the training set, the decisions you are getting on the training sets, and you can find out that uh, what is the covariance matrix, and also whether it is diagonal only or not. If it is diagonal, though, it is independent. Otherwise, you can compute, you can see that how your variance is going to be reduced with this factor. And you can see that negative correlation in this case is as if that it will improve variance, but as you understand that since learners are going to give both are going to give at least more accuracy, more than 50%. So it's not, you should not expect that they should be negatively correlated. There is another interesting way of combining this or making this decision fusion, and it's kind of the idea is borrowed from error correcting code. So uh, let me explain that. In this case, what we are trying to do, that means we are trying to eliminate the outliers of the decision or noise in the decision making process. That means suppose you have uh, L learners, here it is shown as L classifiers, and suppose there are K classes, right? Now, uh, every learner here, what it does, it considers they are performing different tasks. First thing is that they are performing different tasks. So they are not performing identical tasks. So how these tasks could be different? For example, since you have K classes, you can consider, you can choose one of them as the is lying as the positive, as the class denoted by uh, say class 1, and the rest of the samples of other k minus 1 classes, they belong to the other class. So always you are considering a binary classification task. For each learner, you are giving a new binary classification task. So there could be, if there are k classes, um, so rudimentally what I saw, there should be k learners in that case, but it can be of any combination. That means, for example, out of k, a pair of them would be lying in the positive side, or I should say that hypothetical class 1, and the other k minus 2 classes would be the for class 2. So in different ways you can combine them and you can choose them. In fact, as you can see that if I consider the levels as 1 and minus 1, since there are k classes, so you can have at least 2 to the power k number of levels. So you can have 2 to the power k number of such tasks. The way I have I described, because there are trivial classifications of having all of them 1 or having all of them minus 1. You can leave them. So you have 2 to the power k minus 2, right? So that many tasks are possible. Now, when you are taking a decision, what you are observing, now actually you have k classes. So for each class, you are expecting that would give you a kind of unique signature. For each class, for certain, as you understand that for each class, for certain learners it will be +1, and for certain learners it will be -1. That is the signature of that class. But since there would be error, you won't get exactly the same signature. So what we are doing, like error correcting codes, we are grouping them into, we are trying to provide a signature for a class and try to maintain the distance between encoding of two classes, signatures of two classes with certain distance, like Hamming distance, you can measure with respect to Hamming, that how many places they differ in such a way that if one of the decision is at least one or two of the decisions are wrong, then at least you can correct it. So because no, they are near to the encoding of the particular class. I'm not sure whether how much I have made it clarify you, but if you read the error correcting codes principle, then you will find it. I will just give you one example with that example, this may be a bit more clear. So I was just mentioning that in this case, you can consider for each class, there is a signature, means the outcomes of every task, what is already assigned, assigned task, that becomes the signature of a class. So which means, depending upon tasks, I can, I just mentioned. So this is example. So this is these are the designed tasks. You can see that every column here is representing so there are 7 learners. So every column is representing a learner, and this learner is performing this task. Suppose there are 4 classes, so you see that it considers identifying, assigning, suppose this is first, second, third, fourth. So fourth class will be assigned class 1, and the other 3 classes will remain in the class 2. So this is the way it is doing classification. So samples of class 1 and all other samples of, sorry, class 4 and all other samples of class 3, they will remain into, they will belong to different hypotheticals. So this is the task this learner has learned, and ideally, for I should say, I mean, ideally, if any class 1 sample belonging to class 1 occurs, it would give -1 for like that. Now, similarly, this is for the second learner's task. This is for the third, fourth. So third, fourth, fifth, sixth, seventh. Right? So these are the way the learners have been designed. But what about the class identity? Now each row is providing you the class identity, which means if I have a sample, I will apply the learner on for the sample, each learner for the sample, and find out, observe what is the output. Suppose this output is always -1 for all the learners, then I will decide that it is of class 1. Similarly, I will do for class 2, I will do for class 3, and I will do for class 4. But what happens? Suppose there is an error. Suppose this becomes, say, class 1. Now, there is no code which will have all these 3 -1, this -1, class 1. You can see these are the only codes for every class. But then which code is nearby this one? So you can take the distance between that is what is Hamming distance. Hamming distance is so the corresponding code of the class, which is of minimum distance, you can assign to that. Now, in other way, actually, this equivalently, you can also perform, it's a simpler way of doing, instead of doing all those things. It's basically the equivalent computations. What it does, you are simply multiplying. So these are Wij is the element of W. Multiplying with the decision, you can see that if it is correct, then it will be positive, otherwise it will be negative. So for any correct decisions, this value will be positive, because suppose it is in the weight, and also you are expecting the value would be also -1. So naturally that would be positive. And for any correct wrong decision, it will be negative. So for yi, the value, ultimately the value of yi will indicate how much correct is that value, right? And the maximum yi out of that, so when almost in every cases, when it matches, the maximum yi will give you the corresponding class identity. You can use also Hamming code or Hamming distance based classifier, what I mentioned. So just to note here, as I considered that, as I mentioned, that this task should be as different as possible. Here we can see that you have defined 7 tasks for 7 learners, and they are all different. And that is how they are complementing. So the tasks to be learned by the base learners to be different, and predefined tasks may not be simple to learn. That is another problem that I mean, it may be that you have to randomize these tasks, and you have to see what is the performance of a learner. Then only you can select a task. So there are issues are there, of course, when you are selecting a task for the purpose of this. So as I mentioned, this is the decision process. Like when you are using, for example, posterior probability, you can just use this kind of translation, just this a trick that no, suppose the learners are giving output in terms of class posterior. As you know, the probabilities they lie within this interval 0 and 1. But no, in our decision making, it is convenient to handle -1 to 1, as I mentioned. In that case, you can do this simple translation, transformation of with using Pj. So like dj is twice Pj minus 1. You can see that range would be in that case -1 to. So this is one kind of approach what I discussed, where you can have multiple learners and kind of, I should say, complementing each other. But you are applying it's a kind of global approach. You are applying all of them at the same time on a sample, and then finally you are combining them. When you are talking about bagging, what we discussed earlier also, that you are generating different learners, but each learner is um, slightly different. I mean, they are trained on a slightly different training set. So the approach of learning is same, but whereas you are uh, you are providing variations on the training data because models are data dependent. So you get different training, different models. So we are in this way, you are trying to reduce the variability, data dependency, or trying to reduce the trying to avoid the overfitting problems or data dependency on the models. Overfitting is not only data dependency, its model complexity is also there, but let us call it data dependency. So uh, as we say that models are of similar structure and mathematical form, but with different sets of parameters, each base learner. And when you do that, the usual procedure is that your training sets are randomly sampled, and randomly sampled will sampled with replacement, which means the same training sample may occur in multiple learners. So this is what is meant by that. You can use both for both classifications or regression tasks. Right. So here we would like to maintain that no, if your small change in data causes large variation in the model, then learning is unstable. That is a kind of no, you can see that decision trees ANNs are unstable, for example, with respect to this kind of model. So that's why you can have certain kind of aggregation. That is the approach for bagging. Whereas in boosting, you can generate the complementary base learners. I just mentioned earlier also, like you can train the next base learner from the mistakes of the previous learners, uh, where bagging is left to the chance factor and instability of training algorithm. So bagging may be effective, may not be effective. But in the case of boosting, you are trying to make sure that at least your learners are complementing each other. So that is the way boosting. No, that's the philosophy of boosting. That uh, you are trying to give certain kind of guarantee of learning. That means at least the easier samples are learned, and then hard samples, which are as it is difficult to learn, you are processing them later, and you are taking a decision by knowing the fact these are hard samples. So in this case, usually what we do that we can have a series of weak learners, and uh, each learner can have certain weights. We'll discuss the approach. Like we call it a weak learner, which is working slightly, marginally above the margin of 50% of accuracy, or error probability is just below half. So that's the kind of weak learner. So a strong learner is, of course, where you have very high accuracy or very low error probability. So those and um, we'll discuss about two boosting algorithms. Today, I think I will just leave with the one algorithm, and then in tomorrow's class we'll continue this discussion. So there is an algorithm for the boosting algorithm, which was originally proposed. That is the first algorithm which was proposed. It's a combination of 3 weak learners. So it would give you the, uh, give you the principle based on which these algorithms are designed. So you can see that how the decisions are taken in a in this combination. So like exploiting the confidence of the learner. Say you can say, for example, you can divide the training samples into 3 sets, X1, X2, and X3. As you can see that each one will give you 3 different learners. But what we do that train the um, D1 with X1. So basically D1 is the model. Here X1 is the data. So please note my convention. D1 is the model. So D1 is the first model. It is trained with X1, but you are testing that with X2. Okay. So by doing that, you can find out that which are the easy samples of X2 which can be also accepted by D1. So what you do, form a training set X2 prime for training D2 such that which are misclassified by X2. So only the samples which are misclassified in X2, misclassified by D1 in X2, those are considered for training this sample D2. So you understand now that no, but the question is that how do you know when you take a decision it is misclassified? So we'll be addressing that question later on. But let us first. Any questions? Once again. So next, what you do that you train the second model with the X2 prime. Once again, you test it with X3, both with D1 and D2. Now here is the catch. If you find that there is a disagreement, that means train D3 with instances disagreed by D1 and D2, right? So you have 2 models when you are testing with X3, and if you find that there is an disagreement, then only you are training with D3. So you are exploiting this part. So the testing part, what you are doing, if a sample X has same levels by D1 and D2, then accept it, else accept the result from D3. So this was the principle on which this boosting algorithm was designed. As you can see that there is a clear policy of accepting by the learners, weak learners, when they are in agreement. But if they are, so the D3 is kind of a the bit resolver, right? It's so finally, if there is no agreement, then D3 will decide which are going to. That means those samples are much more difficult, and those samples are to be, because you have trained D3 with those instances, so D3 is more specialized on those samples. So in this way, you are trying to uh, make the complementary features of D3 with respect to D1 and D2. So I hope this principle or philosophy is intuitively clear to you. Because there are mathematical analysis, and you may have to go through the original paper to find it out. So with this, today let me stop here, and we'll continue this particular discussion again tomorrow morning's class. And so if you have any questions, let me know. So in that case, let us stop today, and Let us meet tomorrow morning. Thank you very much.